Hi, I'm Tristan, and this is Heisenburg's uncertainty principle. Now, about 100 years ago, a really smart scientist named Werner Heisenburg had this great idea. Using maths, he proved that you couldn't know the exact position of a subatomic object as well as its velocity at the same time. You could either know one or the other, no matter how much you measured it. The reason that you can't just measure a particle and take your answer as the truth is because it isn't only in that one position. Wait, then where is it? Well, subatomic objects are actually in something called a superposition, which means they are in many different places at once, and only by the act of us measuring its position does it randomly show itself in one single place. I know this can be extremely hard to wrap your head around, but try thinking of it this way. If we're here in a room with a balloon floating around, we can pretend the balloon is a subatomic particle. When we aren't looking at it, it exists in multiple places at once. But then, once you start trying to measure it, it pops up into one of the positions randomly. I'm sure you're starting to understand the concept of superpositions. Now let's try with velocities. It's just about the exact same thing. There are many velocities at once for one subatomic object, and it only shows one of them once we measure it. You might be asking yourself right now, why is it called an uncertainty then? The subatomic objects are just randomly appearing, and we have no hope of knowing where they are. Well, actually, we do have a little bit of hope knowing where they are. The reason I've been saying subatomic objects instead of subatomic particles is because things like electrons don't just act like particles, but they also act like waves. And if I were to ask you where this water wave is right now, you wouldn't be able to tell me. You would be able to tell me how fast it's going, but not where it is, because it exists in many different places at once. So, how do we determine the position then if it's a wave? We add something called an interference. This is basically just shooting a bunch of waves that have different frequencies than your original wave, so it turns from a perfectly beautiful wave to a very choppy interference wave. A pulse is what we call these individual sections. A perfect pulse looks something like this, and we can really narrow down the uncertainty in the position, but then we raise the uncertainty in the velocity. The reason we raise the uncertainty in the velocity is because to find the velocity of a wave, you need to know the frequency. And the more distorted the wave is, the harder it is to know that correctly. So, we are able to narrow down the little cloud of where it could appear, therefore lowering the uncertainty of its position. But by doing this, we are raising the uncertainty of its velocity. Waves are tough to visualize, so let's go back to our balloons metaphor. Now, the balloons are still spread out equally through the room, but are not equally in all of the places. Some places are weighted more heavily, meaning that if we measured where it is, it would be more likely to turn up in that one spot. This is also the same when it comes to velocity. Some are weighted more heavily, which means it's more likely to turn up going that speed when we measure it. So, in conclusion, the more you know about the position of a subatomic object, the less you know about its velocity. And the more you know about its velocity, the less you know about its position. And that's Heisenberg's uncertainty principle.